Welcome back. In our last lecture, we covered the scientific method and its importance in shaping good, solid research. And broadly speaking, the scientific method can be divided into two styles of scientific inquiry to help us know what is true. One of these methods is called historical science, and it's used to examine existing evidence and past occurrences to draw deductions. The problem with historical science is that conclusions are closely tied to the perspectives of the observer, and it can lead to erroneous conclusions if it's unchecked by other modes of inquiry. The other method is called experimental science, and it relies fairly heavily on the concept of empiricism. It says that in order for something to be considered scientifically true, we need to be able to use observable, testable, repeatable, and falsifiable experimentation to draw such a conclusion. In the context of something like physics or chemistry, this is pretty easy. If we discover a property of something, we should be able to demonstrate that same property through repeated observation and experimentation. Pure water should always freeze at 32 degrees Fahrenheit or 0 degrees Celsius. Gravity, at least on Earth, should always result in something we drop to the floor falling in a straight line downwards within a predictable amount of time. The color spectrum of a rainbow should always start from the outside with red, then orange, then yellow, then green, then blue, then indigo, then violet. These are all scientific facts that can be observed to be true, repeatedly demonstrated, tested against alternate theories, and if they're not true, can be falsified against alternative evidence. The biggest drawback of empiricism, however, is that things that cannot be tested also cannot be accepted as scientifically true without some hand-waving. These ideas wind up being speculative, theoretical, or axiomatic, all of which are classification for concepts that can't be tested, but which are important to our understanding. Now, I'm not going to tell you that one or the other of these methods is better or right. I hope at this point in your education you're smart enough to realize that science needs to consist of both historical and experimental methods in order to function. And whatever divisions there are in scientific fields between these two philosophies, and believe me, those divisions do exist, the best scientists make use of both. What I am going to tell you, however, is that marketing research tends to be an offshoot from the social sciences, which are in turn derived from a philosophy of science called positivism that combines the two styles of scientific inquiry that we just discussed to some degree. Positivism splits methods into the experimental and non-experimental categories, and then further breaks down non-experimental methods into three further categories: statistical methods, comparative methods, and case study methods. By the way, another name for a non-experimental method in our previous lecture was observational method. Now think about how you've learned about marketing research up to this point, and it starts to make sense. Causal research is experimental. Descriptive research, which relies on using statistical inferences, is descriptive. And exploratory research is comparative or involves case studies. In the positivist approach, experiments are preferable, which is why they sit at the top of the hierarchy, but they're hard to employ in social science because of practical and ethical issues involving human research. Statistics are the next best approach. They sit a little bit lower on the hierarchy, but they're still above these other methods. They allow for generalizations and inferences regarding populations that can predict behavior without being strictly causal. Comparative methods and case studies can be used to develop a contextual understanding of a field of study and to test or refine theories. All of these approaches have a place within the scientific method, and while there's a hierarchy to them, all of them are needed to provide a well-rounded perspective on any field of scientific inquiry. Now, one of the central tenets of positivism is that the world around us is filled with truths that sit outside our immediate perceptions, and these truths are what we might call regularities or laws. One component of this, actually kind of a precursor to positivism, is called naturalism, and it's an approach which is less concerned about studying the minutiae of individual items and more about trying to understand the bigger picture, the general rules that describe how things function. Another component of that is the idea that empirical knowledge, which is knowledge that comes from sensory experience, which could be measured and confirmed through observation or experimentation, that empirical knowledge is superior to what we call normative knowledge, which is essentially the traditional way of thinking, and that way of thinking exists because that's the way we perceive things ought to be. Positivism and naturalism, its earlier offshoot, are fairly easy to understand if you think about astronomy. And particularly, we're going to talk about Copernicus and Galileo, who were early naturalists, who had very positivist kind of views. Now, in Galileo and Copernicus's day, the normative thinking, and this went all the way back to Aristotle and Pythagoras and to really even ancient Babylon, was that the Earth was at the center of the universe, and that all of the heavenly bodies in the sky rotated around it in perfect concentric circles, perfectly ordered, set there in place by God or the gods. And this tradition held for 2,000 years. But in this conception of the universe, this is what we call a geocentric representation. You can see the Earth at the center, and then the Moon, and then Mercury, and then Venus, and the Sun, and Mars, and so on out. In this conception of the universe, there were problems once the observational science kicked in. For example, there were times where when the planets were going in their perfect circles around the Earth, that they would kind of appear to stop or even go the wrong way just a little bit before they got back into their orbit. And this problem was kind of vexing, and the Greek astronomer Ptolemy came up with an idea called epicircles. They were these little subcircles in their orbits that the planets would just go into. And he used that to explain why the planets exhibited such strange behavior. And that was the conventional thinking for a long time. The reason that this conventional thinking was required, that this little excuse was made, and there were many other excuses like this that were made for other strange behavior that were observed in the skies, was that geocentrism made sense to the cultures of the day, and it helped the astronomers of the Greek, Roman, and medieval eras feel like the skies lined up with the scientific and religious thought of the day. And you have to remember that in that time, science and religion went hand in hand. They were both tools for explaining how the universe worked. The normative knowledge was simple. The Earth is at the center of the universe, and the Sun and the Moon revolve around it because, of course, they do. The center of the universe has to be the Earth because that's where we are, and we were created by the gods, and so we're important. And the stars in the sky and everything else there, they were just set there for us to look at and to guide us and to give us perspective. But throughout the millennia in which geocentrism ruled, there were many dissenting voices who felt that we lived in what's called a heliocentric universe, which is one where the sun is in the middle of the solar system and the planets and the stars rotate around it. Now, two notable scientists who proposed these models were Nicholas Copernicus and Galileo. Copernicus was a mathematician and astronomer, and, in the true meaning of the phrase Renaissance man, he was many other things as well. But he began to question the ancient Greek view of the universe. Now, he didn't do this out of any kind of malice towards the thinking. He just started compiling numerous sources of data, saw that they didn't line up with the model that was proposed, and instead argued that the universe could be much more simply explained if the sun were at the center of it rather than the Earth. And that the reason that the sun, the moon, the planets, and the stars appeared to swirl around the Earth wasn't because the Earth was at the center of the universe, it was because the Earth was spinning while it was in orbit around the sun. And this explanation helped make sense out of a lot of the stranger things that were being seen by astronomers as they were looking in the sky. The problem was that, so far as the authorities of the day were concerned, this was tantamount to saying God never created the universe. And, since the authorities of the day in Europe were heavily influenced by the Roman Catholic Church, questioning their authority on matters of religion or science was a dangerous idea, and Copernicus's ideas were seen as a dangerous doctrine. In fact, believing in them was tantamount to heresy. They were people that advocated it were called heretics. After all, it was plainly obvious to anyone living in that era that they could, with their own senses, go out and look at the night sky and see that we were living in a geocentric universe. The evidence was there. Why would a man like Copernicus be needed, or even feel bold enough to dare to challenge the wisdom of the ancient Greek astronomers whose view of the universe fit so cleanly in with what was believed to be true? Now, I'm telling you this from a perspective of people in the 21st century who know that geocentrism isn't true. And we know that in part because of the work of another astronomer, that was Galileo. And while Galileo contributed a lot in science to science in general, what he's remembered for best probably are his telescopes. If you're not talking about his theory of heliocentrism, his telescopes were a big deal. And they could magnify images up to 30 times, and they allowed him to explore the night sky in ways that had never been possible before. He was able to see craters on the moon. He was able to see a sunspot on the sun. He was able to see 3 of the moons orbiting Jupiter, and nobody had even known that those existed prior to him seeing those. He was able to detect the movement of the planets with far more precision than had ever been available before. And through his measurements, he found strong evidence that the normative knowledge that had been handed down for thousands of years was incorrect. The church was so concerned with this threat that to his normative knowledge and the power that came with that normative knowledge, that it forced Galileo to stop his research by putting him on trial for heresy, placing him under house arrest for the remainder of his life, and banning his work from further distribution. But the great thing about scientific knowledge that's based on empirical evidence is that once it's been introduced to the world, it's very hard to ignore it. Now, Galileo, by the way, didn't stop his research. He just stopped publishing it. But the word was out, and one of his contemporaries, an astronomer named Kepler, found evidence that celestial objects traveled in not concentric, perfectly circular orbits, but elliptical orbits, thus explaining some of their seemingly strange behavior. Kepler also introduced ideas from the burgeoning field of physics to the field of astronomy, becoming, in the words of Carl Sagan, the first astrophysicist and the last astroastrologer. Later on, when the very notion of heliocentrism was disproven in favor of a universe in which every star was its own solar system and the Milky Way was one of 100 billion galaxies, it wasn't due to normative knowledge, it was due to empirical knowledge gleaned from an amazing set of scientific advances. It took 2,000 years to dispel the idea that the Earth was the center of the universe, but it only took another 200 years or so for humanity to really, truly begin to understand the scope and scale of the universe, and then another 100 beyond that before we were sending people into space. And what I want you to take away from this little illustration is an understanding that science is more than just experiments. It's more than just observations. It's more than just deduction from evidence. It's also more than just a few statistical tools that you learned how to use in a graduate program. Science involves asking questions in a structured manner, looking for answers that are true no matter what the observer is seeing or where the observer is standing, and then seeking out universal principles that can inform future research. Well, in theory anyway. We'll get to that in just a moment. Now, in this class, we're going to learn techniques that can be used for science, and they can also be used for pseudoscience. And I want you to think very carefully about using them as a means of acquiring useful information that has some scientific weight and rigor to it, and not just for gathering a bunch of data to appease a client's insatiable desire to know the unknowable by listening to as many opinions as money can buy. Because let me tell you, one of the things that bad research does, and that pseudoscientific research does, is it affirms normative knowledge because it becomes so interpretive, it becomes so rooted in the conventional thinking of the day that it doesn't challenge, it doesn't disrupt, it doesn't come up with new ideas. And when it does, they're very easily shot down. But if there's rigor behind what you do, if you really apply the scientific method properly, if you really understand the philosophy behind it, you can do a good job of producing good, truthful, useful information that will help your clients to make the right decisions if you're a marketing researcher. Now, by the way, if you're really interested in learning more about the philosophy of positivism, I should caution you that 21st century science has moved on to a philosophy of what we're going to call post-positivism. And this revised philosophy actually has a lot of relevance to marketing research, particularly when we begin talking about the idea that perception and reality can be really two very different things. Now, to summarize the ideas of post-positivism, we've basically reached a point where science acknowledges that all observation is fallible, and that all of our theory is reversible. Modern science was enamored with the idea of all of the complexity of the universe being boiled down into one cohesive equation or set of equations, but, you know, we realize now that things maybe aren't as easy to reduce down to simple laws as we once believed, and even ideas that hold true for us in our everyday lives are due to forces we can't see or understand at extremely small levels, behaving differently than we'd ever have imagined. And if you want to know more about that, I would suggest you study the field of quantum physics, where all bets are off about the physical laws that we think we understand. I would argue that to a post-positivist, science is less about uncovering what we call universal truths and more about constantly revising our understanding of what is actually true. This doesn't mean that the truth is relative. What this means is that we can never quite reach the truth, but we're always approaching it ever more with the science that we conduct. And that not only fits in with modern methods of scientific inquiry, but it also makes what we deal with in marketing research, where human behaviors and attitudes and environments and culture and context are constantly shifting, it makes them a little bit more understandable. We can find truth, we can look for truth, and we can find it, but there's always going to be a little bit more nuance that helps us understand it that much better. Now, with all that said, post-positivism is such a big topic that's so far outside the scope of this class, I'm just going to encourage you to put it on your list of topics that I'll learn more about when I'm finished with grad school. And by the way, by the end of this lecture series, I'm going to give you a few more of those. But where does that leave qualitative and quantitative? These two labels are extremely important as well, and they don't cleanly line up with our positivist hierarchy, and there's a reason for that. Qualitative and quantitative research, as we use them in the social sciences, come from different fields, and their usefulness has as much to do with how they're being used as who's actually using them. History plays an important role here, and as I'll discuss in our next lecture, these two methods of research are like long-lost twins separated at birth that grew up in separate disciplines and which still have trouble coming together as a result of it.